All right, welcome. This is part 2 of our video series on buffers, our second of our secondary topics in equilibrium. So in this video, we've already talked about what do buffers do, what are the components of a buffer, and why do buffers work. So in this video, I'm going to be talking about the last 3 points, how to pick the best buffer for the job, how to make a buffer, and there are actually 2 ways to do that, and then rounding out with calculations involving buffers. So what makes a good buffer? How do you know if you have a good buffering system? The absolutely key thing is that you have large amounts of the 2 components of a buffer that you need. So you have large quantities of both your weak acid and the conjugate base. Now, equal concentrations is actually ideal. That gives us our best buffer, which is one of the things that you saw in the buffer POGIL. And the reason is due to the equilibrium expression for a weak acid. So our weak acid equilibrium expression, which hopefully you're used to by now, Ka equals H plus times A minus divided by HA. Well, if the HA concentration is equal to A minus, right, if HA equals A minus, then these 2 things will cancel out, right? And if they cancel out, then we have, we wind up with this expression, Ka equals the concentration of H plus, right? If A minus is equal to HA. And if you simply take the negative log of both sides, then you wind up with this expression, pKa is equal to pH. And that actually becomes a critical thing about making a good buffer. If you have equal quantities of both your strong or your weak acid and its conjugate base, then you're going to wind up with this situation right here. Buffers work best when the pKa of the weak acid component of the buffer is equal to the pH of the buffering system. The reason is, if the pKa equals the pH, then you have equal quantities of HA and A minus. Why do you want equal quantities of HA and A minus? Because of this point right here. Why do you want equal amounts of them? Because a buffer, by definition, protects against changes in pH. Well, what could change a pH? A strong acid could change pH, or a strong base could change pH. You want your buffer to be able to protect against both of them. So you want large amounts of both the weak acid and the conjugate base. And if you have equal quantities of both, then you know you've basically got an equal shot of protecting against either the strong acid or strong base. If you have more weak acid, then you're going to be better in your buffer system, then you're going to be better protecting against a base being added in. If you have more weak base in your buffer system, you're going to be better at protecting against a strong acid being added in. The buffer wants to be good at doing both. So it's best at doing both when you have equal quantities of both the weak acid and the weak base. And when that is true, you have this situation right here when pKa is equal to pH. And that's actually going to be crucial for us in recognizing that we do indeed have a buffer system and that we have a good buffer system. Adding strong acid, strong base to a buffer with this equal quantities, right, equal amounts, which is what this middle one is showing, of both the HA and A minus. So we have equal quantities of both. We can protect against both situations. If we add strong acid, which is what this one is saying right here, but if we add strong acid, then we slightly shift the ratio of the HA and the A minus, and we do have more HA, but we see that the ratio has not really changed very much. So we have, if we add some strong acid, now we have slightly more HA than we do A minus in the buffer, but we still have about the same ratio. If we add some strong base to the buffer, now we're going to have more A minus, right? Because we're going to generate that A minus. But again, the ratio does not change very much. The ratio is still about the same amount of A minus and HA, and that's why we kind of want to start with having equal quantities of both. If the ratio between HA and A minus does not shift, the pH will not change very much. It's about that ratio. Now, the ratio can actually be calculated and determined through the Henderson-Hasselbalch equation, or what I like to abbreviate as HH. So the Henderson-Hasselbalch equation, which you have seen in the buffers POGIL, which is on your reference table, by the way, is pH is equal to pKa plus the log of the concentration of A minus divided by the concentration of HA. The Henderson-Hasselbalch, it just straight up comes from a rearrangement of the Ka expression. That's actually really all it comes from. It's like if you take the Ka expression, rearrange it a little bit, and start taking negative logs of things, because you know you've got pH and you've got pKa, which is just the negative log of H plus and the negative log of Ka. That's really all. So this comes directly from the equilibrium expression. We can calculate the ratio of A minus to HA, because this is the ratio of A minus to HA right here. I mean, that is a ratio. So if a problem asks you to calculate a ratio, boom, right, that's all it is. It's right there. It's right there in front of it. Solve for HA, solve for A minus divided by HA, and then you're good. And this expression is once again telling you that if A minus is equal to HA, if you have that situation where you have equal quantities of both, which is where we get our best buffering systems, then A minus divided by HA is going to be equal to 1. The log of 1 is 0, so this entire portion of the Henderson-Hasselbalch equation goes away. And again, you have that the pH is going to be equal to pKa. So this is kind of telling you again that if you have equal amounts, then pH is equal to pKa. Now, you are free to use the Henderson-Hasselbalch equation to solve equilibrium problems from this point forward. The critical point, though, is that you only use it when you can use it, and you can use it if you have HA and A minus. So you have to have a buffer. So you can't use this to solve KSP problems. That is not a buffering system. And you can't use it to solve a weak acid pH problem if you don't have any conjugate base. So you have to have both. You have to have both HA and A minus in order to use this. You can't really work with this unless you have a buffer system, unless you have both a weak acid and its conjugate base. What makes a good buffer? Well, we've been saying that good buffers have both weak acid and conjugate bases in solution, and when they have equal quantities, that's when they're best. And when they have equal quantities of both the weak acid and the conjugate base, then the pH of the buffer is equal to the pKa of the acid component of the buffer. So what we get from that is a totally typical AP problem about buffers. It says a chemist needs to make a solution that's buffered at a pH of 4.3 and can choose from the following acids and their sodium salts. So we're assuming that we have the weak base component, and we have chloroacetic acid with a Ka of 1.35 times 10 to the minus third, benzoic acid with a Ka of 6.4 times 10 to the minus fifth, and hypochlorous acid with a Ka of 3.5 times 10 to the minus eighth. Which acid and its sodium salt should the chemist choose? It goes back to this idea that we want the pH of our system to be as close to the pKa of our buffer as possible. And what did they give us? Boom! They gave us Ka values. So if we simply take the negative log of these, we can figure out which one is going to be closest to the pH that we want to buffer. So the pKa of chloroacetic acid of this value is 2.87. That's kind of far away from 4.30. The pKa of benzoic acid is 4.19. Huh, that's pretty close. And the pKa of chloroacetic acid is 7.46. Ooh, that's very far away. So which buffer do we want to choose along with its sodium salt, which would give us the weak base to make, which acid do we want to choose to make this particular buffer? We want to choose the benzoic acid. We want to choose the benzoic acid because this pKa value is closest to the pH that we want. And the reason that we're choosing it, because it's got the pK that's closest to the pH that we want, will mean that we can have lots of both the weak acid and the conjugate base at that particular pH value. It means we're going to have loads of both our weak acid and our conjugate base. And that's what a good buffer needs. A good buffer needs a large quantity of both. So by picking the buffer that has the pKa that is closest to the pH, that tells you you're going to have lots of the two components of the two necessary components of the buffer. We also have problems like this. So consider these two buffer systems. We have HF and NAF in both. The distinction is in the concentration. So in this first buffer system, we have 0.35 molar in both, and in the second, we have 0.0035 molar in both. Both of these are buffers. Both of them are the weak acid and the conjugate base. So that's going to be, in this case, HF and F minus, right? Because NaF is going to completely turn into Na plus and F minus. So F minus becomes, that's our conjugate base in this particular system. Both of them would have a pH that would be equal to the pKa, because in both of these buffering systems, they have equal amounts. Equal is a better word than same because they don't have the same amounts, but they have equal amounts of the weak acid and the conjugate base. So in both of them, because they have equal quantities of HF and F minus, pH will be equal to pKa. However, there's one of them that is going to be a substantially better buffer than the other, and that's the 0.35 molar buffer. So the 0.35 molar buffer is going to be a stronger buffer. Sometimes we say it has a higher buffering capacity because it has more moles. So the one with a higher concentration, although both of them would have pHs equal to pK because both of them have equal quantities of both HA and Na-, the one with the higher concentration will have more moles of HF and, in this case, F-, so it's going to protect against more strong acid or strong base from being added to the buffer. So yes, they're both buffering systems. Yes, both of them have pHs equal to pKa, but one of them is going to be better at protecting against added concentrations. So looking at this ratio, pH is equal to pKa plus log of A minus over HA. Well, when these two are equal, which we've been saying, right, if A minus and HA are equal, which is the middle one, then A minus over HA is equal to 1. And this diagram is simply showing that if you have exact equal quantities of both in solution, 16 A minus and 16 HA, then you get this situation right here, pH is equal to pKa. Well, what if you don't have that, which is honestly going to be probably more often the case? So let's look over here. What if you have more of the weak acid in solution than you do the strong base? So what if you have 24 HAs and only 8 A minuses? Well, that's going to mean that this fraction right here, this ratio, right, this is a ratio, is going to be less than 1 because we have a larger denominator. We have more HA. That will mean when we plug in a value and take the log of something, a number that is less than 1, you wind up getting something negative from that. So we get a pH of our solution that is less than the pKa of the acid component of the buffer. This will mean, I mean, if you think about this, this should make sense. Our pH is more acidic, right? It's lower because we have more weak acid. So if the pH of your buffer system is more acidic than the pKa of the acid component of the buffer system, that tells you that you actually have more of the weak acid in solution than you do the conjugate base. You don't have same quantities, because if you did, pH would equal pKa, but if pH is under pKa, that actually means that you have more of the acid component. And then looking at the other side, well, what if you have more of the weak base component than the HA? So again, our little particle diagram is showing us that what if we have 28 A minus and only 4 HA? It's still a buffer, but now the A minus divided by HA, now this number is going to be greater than 1. Again, this is our ratio. It's going to be greater than 1 because we have a larger numerator, right? More A minus. If you take the log of something, again, back up here in the Henderson-Hasselbalch equation, of a value that's greater than 1, now you get something that's positive. So now you're taking pKa and you're adding something that's positive to it. Now you wind up with this situation where the pH of the buffer is greater than the pKa of the acid component. Again, this should make sense because now this is saying that our pH is more basic than the pKa of the buffer on its own. And then the reason is because we have more of the weak base, right? More A minus. So having more of the weak base component of the buffer pushes the pH up a little bit. So you can tell simply by examining how pH and pKa compare to one another if you have equal quantities of both the weak acid and the conjugate base, or if you have more weak acid than conjugate base, or if you have more conjugate base than weak acid. And it's all down to this particular ratio. Making a buffer. How do you make a buffer? There are two ways. There's the easy way, and then there's the slightly more complicated way. The easy way is very simply, hey, let's take a weak acid and let's take its conjugate base and let's put them in the same beaker. That's the easy way to make a buffer, because that's kind of like the duh. If a buffer needs two components, then why don't we just put those two components in the same beaker and then you have a buffer. The slightly more involved way is something called half titration. It also works, and it's basically like, what if you don't have a pair? What if you go to the chemical storeroom and you have the buffer that you want to make, but you realize you don't have both components of the buffer? You only have, let's say, one component of the buffer. You can still make that buffer, if you know what you're doing, by using this half titration method. So it's about, if you don't have both parts of the pair, you can actually make the other part of the pair through an acid-base neutralization reaction. The idea is, it's called half titration because let's say you have HA but you don't have A minus. Let's titrate half of our HA. Let's literally split our weak acid solution into two equal portions and take half of it, and let's react half of it with a strong base. And the reason we're reacting it with a strong base is because then we get this reaction to occur. HA plus OH minus, that's the strong base, makes A minus plus H2O. This reaction is one way. It is not reversible. It goes until something is completely used up. So you kind of want to be careful there and use up both your HA and your OH minus. So again, we've taken half of our HA and we've undergone this particular reaction. The reason why we did that, because this reaction, it made this. Ooh, it made A minus. Ooh, yes, it did. Oh, so we didn't have one of the components of the buffering system, right? We only had one. Ooh, you can make the second one by reacting some of it, because once you've created that A minus, if you then recombine it with the half of the HA that you left untouched, remember, we took half here. We didn't react all of it. We split it into two equal portions. We reacted half of it, and then you combine it back together. Ooh, now you have both of them together in the same beaker. Yes, you do, and there is your buffer. Now, when you do this, there are some key points about this. You cannot have excess strong base, meaning like you can't have more moles of strong base than you do weak acid. So you have to be very, very careful with how much strong base you add. You have to sort of react it exactly so that you don't have any extra hydroxide swimming around, because if you do, then you run the risk of using up all of your HA, which you do not want to do. You need both HA and A minus, so you have to keep some HA unreacted. So just enough for some, not all. And we can use this exact same idea if you only have a weak base. If you only have a weak base in solution, then let's react half of it with a strong acid to create the conjugate acid of the weak base, and then recombine it, and then boom, there's your buffer, your weak acid conjugate base pair. So AP loves to ask multiple choice questions like this. Which of the following will not produce a buffered solution? So we want, in order for something to be a buffer, we want the weak acid and the conjugate base pair. And just looking at this, notice we have sodium carbonate in all of them. Now, sodium carbonate is a weak base. So in all of these, we have a weak base. So essentially, we're looking to see if we make a buffer, then we want to also have its conjugate acid. It's the carbonate ion that's the weak base in sodium carbonate, so we want to get that bicarbonate ion. And if we have that, if we have both of them together, then we know we have a buffer system. If I'm looking for the conjugate acid of this, I'm going to right away kind of go to part C and notice that, hey, that's the conjugate acid, and I have 0.01 moles of the weak base, and I have 0.015 moles of the conjugate acid. So I mean, that boom, buffer, right? That is absolute. That's the easy one, right? That's the weak base plus its conjugate acid. That's not going to be our choice because we're looking for the one that does not create a buffer, but like weak base plus its conjugate acid, like that's definitely going to be a buffer. Then we have three other choices that do not have the weak acid conjugate base pair, but two of them will give us a buffer, one of them will not. So what I'm going to do now is kind of work out how many moles of each thing I have from the numbers. So I've got 0.01 moles of the Na2CO3 actually in all three of these cases. And then I'm going to look at what I'm reacting it with. In A, I'm reacting it with 0.005 moles of a strong acid. In B, notice I am saying reacting because there would be some kind of reaction that would take place here. I'm combining it with that. I've got 0.005 moles of a strong base in B, and in D, I have 0.005 moles of a strong acid. Well, looking at A and D, notice they're the same. Notice that you have 0.01 moles of your weak base, and you react it with 0.005 moles of a strong acid. This would make 0.005 moles. So this would get used up, and you'd make 0.005 moles of the conjugate acid, HCO3 minus, in both of these cases. So you'd use up 0.005 moles, and you'd be left with 0.005 moles of CO3 2 minus. And again, this is going to be identical for A and B because we actually have identical quantities. So in both cases, I'm sorry, A and D, we wind up with a situation where we have, this is our half titration method, equal moles of both the weak acid and the conjugate base, or in this case, the weak base and the conjugate acid. So we actually have a buffer in both of these situations. That's that half titration method. But if you look at B, what's different about B is that you have a weak base plus a strong base. There is absolutely no way that you will get a weak acid out of that situation because you have a weak base and a strong base. There is no weak acid. So you're not going to be able to make a buffer any possible way you can think of from that. So B is the one that's not going to make a buffer. Buffer calculations, they're really just common ion calculations. That's all they are. So reaction ice chart, expression, solve, same situation as always. But the thing that I will say now is that we can also use the Henderson-Hasselbalch equation if you have both your HA and A minus present. So a simple buffer problem, calculate the pH of the buffer. There's 0.12 molar benzoic acid and 0.20 molar sodium benzoate using the Henderson-Hasselbalch equation, which is here. So thinking about what we have in solution, we have some sodium benzoate. So I'm just going to call that HA because I don't know the formula for benzoate, and sometimes you don't need to know the formula of benzoate. And we know that we have 0.12 molar of it, and you also know that you're going to get some H plus and A minus. So this is me kind of making my list of ions that I have, right? Some H plus and A minus coming off of the HA, right? Dissociating off, but we assume that we start at 0. And then we also have sodium benzoate, so that's NaA. I know that it's also the A because again, benzo is common to both. So this is a group 1 ion, so it's going to completely dissociate into Na plus and A minus. So I've got 0.20 molar of this, so I'm going to have 0.20 molar of that and 0.20 molar of that. And boom, common ion. So I know I have A minus coming from the sodium benzoate in this case, so I know I have a buffer. Now, in order to solve this, we need the Ka value. So you can look up the Ka in Appendix 5, because you would need that in order to solve this problem. So make sure you use that on the problem sets. And the Ka is actually equal to 6.4 times 10 to the minus 5th. And with that, we can really just go right to the Henderson-Hasselbalch equation. So we're looking for pH. And we have HA concentration, we have A minus concentration, and we have a Ka value, right? Our concentrations were given over here, and we looked up the Ka value. So I'm going to just do the negative log of 6.4 times 10 to the minus 5th, plus the log of A minus. Well, what's our A minus concentration? Oh, there it is. That's our A minus concentration coming from the sodium benzoate. So the plus the log of 0.20 molar, divided by, and then the log of our HA concentration. Ooh, what's that? There it is, right there, 0.12 molar. And it's just solving. It's not terribly involved. So I get 4.19 for the pKa plus, and then taking the log of that value, I get 0.22. So I wind up with a pH value that is 4.22. 4.41, which is the answer to the question. Now notice the pH in this case is greater than pKa, right? 4.41 is greater than 4.19. The reason is because in this case, the weak base concentration is greater than the weak acid concentration, right? The 0.2 over 0.12. So our pH is slightly more basic than the pKa because you have greater quantities of your weak base than you do your weak acid. So there you go, pH of a buffer, not hard. Calculating pH of a buffer might be the easiest part of buffer chemistry. So then just another type of problem, calculate the mass of sodium acetate required to prepare a buffer of pH 4.55 when added to 0.5 liters of 0.67 molar acetic acid, and the Ka value for acetic acid is given. So this is basically going into how do you make a buffer, buffer creation calculations. So thinking about this problem right here, what do we have in solution? Well, we have acetic acid, right? So that's HOAC. And we know we have 0.67 molar of it. And then we know that we're going to get some H plus and acetate ion off of that. And then it's asking us about sodium acetate, which again will completely dissociate into Na plus and OAC minus. So again, the reason I'm doing this, pointing out that this is our common ion. The acetate ion is our common ion. It's our A minus in our Henderson-Hasselbalch equation. Now looking at the Henderson-Hasselbalch equation, the problem gives us lots of numbers. It tells us the pH that we want. Okay, so that's pH. It gives us the Ka value of 1.8 times 10 to the minus fifth, so that's that. It gives us the molarity of HOAC, so it gives us the molarity of HA, and look at what it's asking for. It's asking for the mass of sodium acetate. We've worked out that the acetate ion is the A minus, so that means that this is going to be our X. That's going to be our unknown, and that's how we're going to approach this problem. We want to solve for mass. The first thing that you want to solve for is what's the concentration of the A minus. So really, I'm just going to plug in and start solving. So 4.55 is equal to the negative log of 1.8 times 10 to the minus fifth plus the log of X over 0.67. Then I get 4.55 is equal to that's 4.38 plus the log of X over 0.67. Then we get 0.17 is equal to the log of X over 0.67. We want to solve for X, so you have to do base number power. So if you take both sides and make them the exponent for 10, you get the log to go away. And I get, what is it, 1.479 is equal to A minus, or X over 0.67. So solving that, you get that A minus, your acetate concentration, is 0.991 molar. But we don't want the molarity, we want the mass. So now we have to start pulling in the other number that the problem gave us, which is the 0.50 liters. We want mass. We can get mass from moles. We don't have moles right now, but we do have molarity, and we do have the fact that it's going to be equal to X moles over 0.500 liters. So we get, when we solve that we want 0.4955 moles of acetate. But we want the mass of sodium acetate, so we know that that's going to be equal to the same value because of a one-to-one relationship shown up here, right? One acetate ion, it comes from one sodium acetate, and I have to erase some work to continue this problem, because the math can get long with this. So I work out that that's how many moles of sodium acetate I want. From this point on, you should be realizing what you need to do to do the last final step. So 0.49, we want mass. 0.4955 moles of sodium acetate. I am using the abbreviation here. But you get the GFM of sodium acetate from the real formula, which is 82 grams per mole. So 1 mole of sodium acetate weighs 82 grams. So solving this, you're going to want 40.6 grams of sodium acetate in the 0.5 liter solution of 0.6, also containing 0.67 molar acetic acid, will give you that buffer with that particular pH. So tomorrow, in our buffer problem set, you're going to be seeing all types of buffer problems, some involving calculations, some not. Make sure you feel confident in recognizing a buffer.